we want to look next at how to find the derivative when we're dealing with parametric equations. Because even though with parametric equations our x and y coordinates are defined with respect to t, our graphing still happens in the xy plane, and we still want our slope to be the change in y with respect to x. Alright? So how can that happen when our equations for x and y are with respect to t? Alright, let's just look at this. X as a function of t, we could write the derivative of that as dx dt equals x prime of t. In other words, that's the change in the horizontal component with respect to time. And y equals a function of t is dy dt equals y prime of t, which is the change in the vertical component. But what we want, as we said, is dy dx. So how do we connect these three derivatives? So let's take dy dt, and through the chain rule, I know that I can write the derivative of a function with respect to a given variable as the derivative with respect to a different variable, and I'm going to choose x in this case, and then multiply the derivative of that new variable onto the original, so times dx dt. And so I've expressed the derivative of this function through the chain rule as so. And as you can see, we now have the three derivatives above related. And so I can isolate the derivative I want, dy dx, which would be dy dt divided by dx dt. In other words, the derivative of y with respect to x is the derivative of y with respect to t divided by the derivative of x with respect to t. So let's apply that formula to finding the slope of our curve defined by these parametric equations at x equals 1. So first of all, I need to know the derivative of x with respect to t. That would be 2t to the negative 1, and by the power rule that would be negative 2 over t squared. And the derivative of y with respect to t would be 1 over t. Therefore, the derivative of y with respect to x would be this divided by this. And if we simplify that, divide, multiply by the reciprocal of the denominator, I'm going to get negative t over 2. Right? So I have my derivative for y with respect to x in terms of t. Now I want the specific slope at x equals 1. So what I need is the t value when x is 1. So I need to find t when x is 1. So I can find the t for x equals 1 by relating that to my equation x with respect to t. So 1 would equal 2 over t, therefore t would have to be 2. And so now I can find my specific derivative, y with respect to x, at the moment when x is 1, which is equivalent to time being 2. Substitute 2 into my derivative, and I get a slope of negative 1. Now, I can use my calculator to get derivatives. I have my parametric equations entered, and my window dimensions, I've got t going from negative 21 to 21, and x and y from negative 5 to 5. So here's the graph of my parametric equation with those values of t. And if I just do trace, I can enter time equals 2, and I can confirm that in fact x does equal 1 at that point. And so there's the point on the graph, and if I drew a tangent slope, it looks like it'd be a slope of negative 1. Alright, so I can get that slope by going second function, calculate, and I want dy dx at the moment when t is 2, and that's giving me negative 1 if I round that off. Alright, remember the calculator sometimes has problems getting it dead on, but that's really negative 1. So now you might wonder, how would we go about finding higher order derivatives? So the second derivative, now I've got to think of the second derivative as the derivative of the first derivative. Alright? And so now what I'm going to do, now that I've got this derivative set up with respect to taking the derivative of my original function, I've got to think of this like the y right here. And so what I'm going to do is I'm going to apply this formula above in the same way. My dx dt is going to remain my denominator, but my numerator is going to be the derivative with respect to t of this function, which in this case is dy dx. This is my formula for second derivative. So let's look at how that works with the parametric equations we have. We've already determined for these parametric equations that the derivative was negative t over 2. So now what we're saying is that the second derivative the numerator part of that is the derivative with respect to t of this. So the derivative with respect to t of this, which is going to be negative a half, divided by my dx dt, which from the previous page was the derivative of this, negative 2 over t squared. Which will equal negative a half times t squared over negative 2, which is going to be t squared over 4.